All right, welcome to today's Explainer. We're jumping right into one of the absolute coolest and honestly most industrially crucial concepts in all of electrochemistry. Today, we're going to figure out how to literally rip chemical compounds apart. And we're not talking about using brute physical force or just cranking up the heat. No, we are doing it by harnessing the sheer power of an electrical current. So think about it. How exactly do we split apart a substance using just electricity? See, in our modern world, we rely entirely on these highly reactive metals, right? Think of things like aluminum. But here's the catch. These metals don't just sit around in nature waiting for us to scoop them up. They are locked away, tightly bound inside solid rock compounds. To get them out, we need a massive, reliable way to break those chemical bonds, and that is exactly what we are unpacking today. Here's our roadmap for the explainer. First, the basics of electrolysis. Second, the movement of ions. Third, the electrolysis of molten compounds. Fourth, the aqueous solution twist. And finally, number 5, the electrolysis lab practical. Okay, let's kick things off with part 1, the basics of electrolysis and defining our terms. Before we dive into the crazy reactions, let's just get our core definition nailed down. Electrolysis is, quite simply, the breaking down of a substance using electricity. Actually, the word itself literally tells you what it does. Electro for electricity, and lysis, which means to split or break apart. But, and this is absolutely crucial, you can't just zap a solid rock and expect it to work. The substance you're breaking down has to be either melted into a liquid or dissolved in a solution. Why? Because its particles need to be free to move around. We call this conductive liquid the electrolyte. Let's set the stage and map out the physical arena where all this splitting magic happens, the electrolytic cell. Up at the top, you've got your power source, like a battery. That battery connects to 2 solid rods that are completely submerged down into our liquid electrolyte. We call those rods the electrodes. One is positively charged and the other is negatively charged. And suspended in that liquid between them, those are our floating charged particles called ions. Some are positive and some are negative. Now, keeping the names of these electrodes straight can be kind of tricky, so here is a brilliant little memory trick for you. PANIC. Positive is anode, negative is cathode. Literally, just remember panic, and you will always know that the anode is your positive rod and the cathode is your negative rod. Simple, right? Moving right along to part 2, the movement of ions, where opposites attract. So our cell is all set up. What actually goes down when we flip the switch and the electric current starts surging through the circuit? Well, before we track where the ions go, we need to know what happens when they actually get there. It's all about trading electrons. In electrochemistry, oxidation is the loss of electrons, reduction is the gain of electrons. When those charged ions finally touch the electrodes, they're going to either lose or gain electrons so they can become neutral, totally discharged substances once again. As for the movement itself, that boils down to the golden rule of the universe. Opposites attract. The positive ions, which we call cations, naturally flock straight toward the negative electrode, the cathode. Meanwhile, the negative ions, the anions, they rush over to the positive electrode, the anode. Once they arrive, those negative ions drop off their extra electrons at the anode. That's oxidation. Those newly freed electrons then zip through the external wire all the way over to the cathode. And hey, here's another great memory trick for you. Electrons flow alphabetically in the wire, from the A node to the C node. All right, section 3, electrolysis of molten compounds. Let's look at a simple application. Let's look at a massive, real-world industrial setup for extracting aluminum. Here's the problem. Aluminum oxide is incredibly stubborn. It takes a completely absurd amount of heat and energy to melt it down. So industrially, we use a really clever hack. The aluminum ore is dissolved into a molten substance called cryolite. Why? Because that cryolite significantly drops the melting point of the aluminum oxide. It's a total game changer that saves vast amounts of energy. Inside this massive steel container, we've got our positive graphite anodes dipped in and a negative graphite cathode lining the entire bottom. The main event is what's happening right at those electrodes. The positive aluminum ions get pulled down to the negative cathode at the bottom. Once there, each aluminum ion gains 3 electrons, meaning it's reduced, and it transforms into pure molten aluminum metal that you can literally just tap out of the bottom. At the exact same time, the negative oxide ions are drawn up to the positive anodes. There, they lose electrons, that's our oxidation, and they bubble off as oxygen gas. It really is a perfectly elegant closed-loop extraction. Okay, get ready for part 4, the aqueous solution twist. Let's learn the rules of the arena. As cool as that aluminum setup is, melting solid rock is still super expensive. For a lot of compounds, it's way easier to just dissolve them in a bit of water. But doing that, it introduces a massive complication. So, what exactly happens when water gets involved? Well, aqueous solutions aren't just the dissolved ionic compound floating around. The water molecules themselves actually break apart or dissociate just a little bit. And when they do, they throw their own ions into the mix, positive hydrogen ions and negative hydroxide ions. Picture an aqueous sodium chloride solution. It is an absolute crowded mess in there. We don't just have our positive sodium and negative chloride ions anymore. Nope, we also have positive hydrogen and negative hydroxide ions crashing the party, courtesy of the water. So the moment you turn on the battery, both sodium and hydrogen rush toward the negative cathode. At the same time, both chloride and hydroxide rush toward the positive anode. But here's the kicker. Only one ion can actually win at each side. There is a literal competition happening. Let's break down the rules of this competition, starting over at the cathode. When you've got a metal ion and a hydrogen ion battling it out at the negative cathode, it all comes down to the reactivity series. And the rule here is kind of counterintuitive. The least reactive element wins. The loser of the reactivity race actually wins the prize to gain electrons and be discharged. So if your metal is super reactive, like sodium or potassium, hydrogen says, I'm less reactive, and wins, bubbling off as a gas. But if your metal is kind of lazy and less reactive than hydrogen, like copper for instance, then the copper wins and coats the electrode as a beautiful solid metal. Now, let's look at the anode competition on the positive side. Here, you've got negative ions from your compound fighting the negative hydroxide ions from the water. The golden rule here is all about the VIPs of the periodic table, the halides. That's your chlorides, bromides, and iodides. If a halide is anywhere in that solution, it automatically wins the competition, and you'll get a halogen gas, like chlorine, bubbling right up. But if there's no halide around, let's say you're using something like a sulfate or a nitrate, then the hydroxide ion from the water takes the crown. It gets discharged, which ends up forming oxygen gas and water. And finally, part 5. The electrolysis lab practical, where we prove all this actually exists. All right, we've talked a whole lot about invisible ions competing and gases bubbling up, but how do we actually prove this in the real world? Well, we trap those gases in the lab and we test them. If your cathode competition produced hydrogen gas, you take a lit splint, pop it into the test tube, and you'll get this highly satisfying squeaky pop sound. If the anode produced oxygen gas, you take a splint that you've just blown out so it's only glowing, stick it in, and it will suddenly burst back into flames and relight. And if your anode produced chlorine gas, hold a piece of damp blue litmus paper near it. It'll briefly flash red because it's acidic, and then the chlorine will completely bleach it stark white. So, bringing it all together, how vital are these electrical braking processes to the modern materials you use every single day? Honestly, they're everything. Every time you unroll aluminium foil or hop on a bike with a lightweight aluminium frame or even just tap the screen of the device you are using right now, you are directly relying on the science of electrolysis. We are quite literally using electricity to split the unsplittable, separating the fundamental building blocks of our world so we can build the technology of tomorrow. It's chemistry, it's electricity, and it's just absolutely essential. Thanks for learning with me today, and I'll catch you in the next explainer.